Well, I think the trouble with string theory is that there isn't any connection with observations. As far as I'm probably taking too strong a view here, but it's largely driven by the mathematics as far as I know, which is in itself is not an objection as far as I'm concerned. A lot of what I do is driven by the math. But the trouble with string theory is it's supposed to be a theory of the way the world operates. And if the number of dimensions of space is just wrong, I can't take it seriously.
But there's something almost paradoxical about this microwave background. It's telling us that there was something like the Big Bang there. But it's also telling us, because the observations of the microwave background, you can plot the frequency, you can plot the intensity against the frequency, and you find this wonderful curve. It's the Planck curve, black body spectrum, and it agrees with that to an extraordinary precision, much better than you could produce in the lab. And this is telling us that the very early universe must have been in what's called thermal equilibrium. Thermal equilibrium, by definition, is the maximum random state. It's the state that the second law tells us we're going to get in the future, if you like.
British mathematician and philosopher Sir Roger Penrose and American theoretical physicist Michio Kaku hold significant positions in the scientific community. Penrose is celebrated for his work on black holes, while Kaku is well known for his string theory. What's interesting, however, is Sir Roger Penrose's strong opposition to Michio Kaku's string theory. Dark matter plays an important role in explaining certain phenomena in the universe. However, Penrose believes that dark matter might not exist at all. So what drives Penrose to reject Michio Kaku's string theory, and why does he assert the non-existence of dark matter? Let's find out. String theory is a theoretical framework in physics that aspires to provide a unified explanation for the fundamental forces and particles in the universe. Essentially, it suggests that rather than point-like particles, as described in traditional particle physics, the universe's fundamental constituents are minute vibrating strings. These strings can oscillate at various frequencies, giving rise to different kinds of particles and interactions. The concept of string theory came about in the late 20th century when physicists sought to reconcile two seemingly contradictory theories: general relativity, which elucidates gravity as the curvature of spacetime on cosmic scales, and quantum mechanics, which deals with the behavior of matter and energy on the subatomic level. String theory emerged as a potential solution by proposing that the fundamental elements of reality are one-dimensional strings that vibrate within a multi-dimensional space. In string theory, the universe is described as having more than the familiar 3 dimensions of space and 1 dimension of time. The theory requires extra dimensions, usually 6 or 7 additional ones, to account for the various vibrational modes of the strings. These extra dimensions, often compactified or curled up, aren't observable at our macroscopic scale and are believed to influence the properties of particles and forces. String theory's notable feature is its ability to naturally incorporate gravity into its framework. Unlike other quantum field theories, where gravity is often treated as an external force, string theory includes gravitational force within its equations. This departure from previous attempts to merge quantum mechanics and gravity is a significant aspect of string theory. String theory also introduces the concept of different string vibrational modes corresponding to various particle types. For example, the various particles in the standard model of particle physics, like quarks, electrons, and photons, can be thought of as distinct vibrational states of fundamental strings. This offers a potential explanation for the diverse range of particles observed in particle accelerators. There exist various versions of string theory, such as type I, type IIA, type IIB, heterotic SO32, and heterotic E8XE8. These versions originate from distinct mathematical formulations of the theory, each having its unique characteristics and predictions. Interestingly, these different versions are thought to be connected through a web of dualities, suggesting that they represent different descriptions of the same underlying theory. Now, let's talk about why Roger Penrose rejects string theory. Roger Penrose is a renowned theoretical physicist and mathematician, known for his significant contributions to various areas of physics, including general relativity, cosmology, and the study of black holes. While Penrose has made groundbreaking advancements in these fields, he has been critical of string theory and has articulated several reasons for his skepticism. Penrose's rejection of string theory arises from both conceptual and empirical concerns, reflecting his unique approach to understanding the fundamental nature of the universe. One of the central criticisms Penrose has expressed about string theory is related to its lack of predictive power and empirical testability. According to him, a fundamental theory of physics should not only be mathematically elegant and internally consistent, but should also make testable predictions that can be confirmed or refuted through experiments or observations. String theory, despite its mathematical elegance and potential for unification, has not yet generated predictions that can be directly tested using current or foreseeable experimental methods. Penrose has pointed out that string theory allows for a vast range of possible solutions and scenarios, making it challenging to identify a unique prediction that distinguishes it from other theories. This lack of specificity diminishes the theory's scientific value in Penrose's view because it hinders its ability to make concrete predictions about the behavior of particles or the outcomes of experiments. In contrast, Penrose's own work, such as his development of the Penrose diagram and his proposal for the cosmic microwave background radiation as evidence for the Big Bang, has been centered on making testable predictions and providing observable consequences for his theories. Another aspect of Penrose's skepticism regarding string theory pertains to its departure from his favorite approach to grasping the fundamental nature of space-time and geometry. Penrose has long championed the concept of twistor theory, an alternative method of describing space and time that he developed. Twistor theory aims to unite general relativity and quantum mechanics by focusing on the geometric aspects of space-time and the relationships between light rays and null geodesics. In Penrose's perspective, string theory places too much emphasis on particle-like entities and their vibrations, potentially overlooking the deeper geometric structure of space-time. He has argued that a more geometric approach like twistor theory might lead to a more profound understanding of the universe's fundamental nature. This philosophical difference in viewpoint has contributed to Penrose's reluctance to fully embrace string theory as a workable framework for unification. Additionally, Penrose has raised concerns about the level of complexity and mathematical sophistication that string theory demands. While he acknowledges the mathematical beauty and elegance of the theory, he has questioned whether its intricate formalism reflects deeper physical truths or if it might be an artifact of the mathematical framework itself. Penrose's own work often centers on developing intuitive and geometrically inspired concepts, and he has posed questions about whether the complexity of string theory might hinder a clear physical interpretation. Furthermore, Penrose's rejection of string theory can be understood within the context of his broader approach to theoretical physics. He has a history of challenging established paradigms and seeking unconventional solutions to fundamental problems. His exploration of the nature of consciousness, for instance, has also faced skepticism from certain segments of the scientific community due to its divergence from mainstream cognitive science. Now, you might be curious about the alternative theory proposed by Roger Penrose, different from string theory. Penrose's alternative is called conformal cyclic cosmology, a distinct and thought-provoking way of looking at the universe that doesn't align with the mainstream ideas of string theory. Conformal cyclic cosmology is a speculative model for the cosmos that Penrose introduced as an alternative to the commonly accepted Big Bang theory, and as a response to the ultimate destiny of our universe. In conformal cyclic cosmology, Penrose builds on his prior work in areas like black hole physics, twistor theory, and his exploration of space-time singularities. At the core of conformal cyclic cosmology lies the concept of conformal geometry, a mathematical idea that maintains angles but alters distances. In conformal cyclic cosmology, Penrose proposes that the universe experiences an endless series of cycles, with each cycle referred to as an aeon. Within each aeon, the universe goes through a phase of expansion followed by contraction. However, Penrose adds a unique twist to the concept of the Big Bang and cosmic evolution. In conformal cyclic cosmology, Penrose suggests that as the universe approaches the end of a contraction phase, the geometry of spacetime becomes conformally related to that of the initial state of the subsequent aeon. This means that the distant future of one aeon is linked, in a conformal manner, to the distant past of the next aeon. This connection ensures that information and structures from one aeon persist and are carried over to the next. One intriguing consequence of this cyclic conformal geometry is the avoidance of an ultimate Big Crunch singularity. In conventional cosmological models, the universe's expansion is believed to be driven by a period of inflation followed by a potential slowdown, leading to a Big Crunch singularity. In conformal cyclic cosmology, the universe's evolution doesn't culminate in a singular point. Instead, it smoothly transitions from one aeon to the next, retaining its geometry and information. Now let's delve into the concept of dark matter and why Roger Penrose challenges its existence. Dark matter is a theoretical type of matter thought to constitute a significant portion of the universe's mass. However, it doesn't interact with electromagnetic radiation like regular matter, making it undetectable through conventional means. Its presence is inferred from its gravitational effects on visible matter, such as galaxies and galaxy clusters, which display behaviors unexplained by observable matter alone. While dark matter is widely accepted in the scientific community as a way to account for these gravitational anomalies, there are dissenting views, with Roger Penrose being a notable skeptic. Penrose's skepticism regarding dark matter isn't about denying the presence of unseen mass. Instead, it involves proposing an alternative explanation for the observed phenomena, usually attributed to dark matter. Penrose's skepticism has various aspects, and it's essential to consider his arguments within context. A key aspect of Penrose's stance is his suggestion that specific gravitational anomalies linked to dark matter, particularly in galaxies, could be explained by his conformal cyclic cosmology theory. In conformal cyclic cosmology, Penrose proposes that these observed gravitational effects might result from the cumulative influence of gravitational radiation originating from distant massive objects over cosmic timescales. According to his argument, this gravitational radiation could create the appearance of extra mass without requiring the existence of non-interacting dark matter particles. So this wraps up the discussion on string theory, Roger Penrose's alternative theory of conformal cyclic cosmology, and his views on dark matter. Let us know what you think in the comments section.